Bismillahirrahmanirrahim. Let's start our next lecture for heat and mass transfer. And this lecture is regarding heat exchangers. This is in fact a very important topic, and the heat exchangers in fact are devices that facilitate the exchange of heat between two fluids. So it may be air or it may be gas on both sides, or we may say that both the fluids may be gases, or both the fluids may be liquids, or it may be one of the two. So it may be gas to gas heat exchanger, or it may be liquid to liquid heat exchanger, or liquid to gas heat exchanger. So heat exchangers are devices that facilitate the exchange of heat between two fluids, and of course one fluid would be termed as hot fluid and the other fluid would be termed as cold fluid. The temperature of the hot fluid of course would be relatively higher as compared to the temperature of the cold one. So the two fluids would be at different temperatures while keeping them from mixing with each other. So they will not be getting mixed with each other. So heat transfer in a heat exchanger usually involves convection in each fluid and conduction through the wall which separates the two fluids. So since the two fluids will not be getting mixed with each other, so there would be a wall between them. It may be a plain wall or it may be a cylindrical wall. So the heat will transfer through that particular wall via conduction, whereas between that wall and the fluid there would be convection. This is a typical shape of a shell and tube heat exchanger. Just to give you an idea that there are different types of heat exchangers. Currently we are looking at shell and tube heat exchanger. So in this shell and tube heat exchanger there is a bunch of tubes that are placed in a large shell. So over here these are all the tubes. These are all the tubes that are placed in this large shell. So there would be one fluid which would be inside the tubes and the other would be outside the tubes, and the one which is outside the tubes may also be called as within the shell. So for example over here it says shell side fluid in. So this is the place where the shell side fluid comes in, and this would be the inlet of the tube side fluid in. So this fluid will enter the tubes. It will enter the tubes. So the fluid will enter the tubes in this particular direction, and then it will come out in this direction. However, the fluid which is outside the tubes, means shell side fluid, will come in and will come out in this particular direction. However, it will not simply come out from right to left, whereas we can see over here that this fluid is being directed in a particular direction with the help of those what we call baffles. So there is a restriction of flow. The fluid cannot move in this particular direction. It cannot move in this particular direction because of this restriction. So it will flow downwards and then of course upwards and then downwards, because there is a second baffle over there, and then there is a third baffle over there, and then a fourth one. So the fluid is being directed in a particular, is being flown in a particular direction, and this is being done, you would have realized by now that this is being done so as to increase the heat transfer rate between the two fluids. And the baffles in fact induce turbulence. Baffles in fact induce turbulence, and turbulent heat transfer is more than the laminar heat transfer. So that is why They make sure, the baffles are used to make sure that the fluid makes a good contact, and in fact it induces turbulence which enhances the heat transfer rate. Moving forward, this is you are being shown the bunch of the tubes. So you can see that there is a large number of tubes that are embedded in this structure, and of course this would be placed in a larger shell. So this is the shell and tube heat exchanger. It has got a lot of in fact applications. The heat exchangers are used in steam power plants when we talk about boilers or condensers, cooling towers, other sort of heat exchangers. They are in fact heat exchangers, they are heat exchanging devices. Similarly, in chemical processing plants, wherever we want to heat something up, so a heat exchanger would be required. Similarly, in textile industries, whenever the boilers are used, and other heat exchangers are used as well. Similarly, in HVAC systems, in building heat and air conditioning systems, we make use of heat exchangers. For example, in not only in air conditioning but in refrigeration units as well, because when we talk about different parts of different components of refrigeration and air conditioning units, so you would have heard of different devices that, for example, evaporator and condensers. So they are in fact heat exchangers. So over here it's a pictorial view of the cooling tower, and probably you would know that there are two types of cooling towers. So but we are not going into the details. One is the forced draft and the other one is the induced draft. So it's in fact a big heat exchanger. Similarly, when we talk about refrigeration and air conditioning systems, so there are evaporators and condensers, and they are in fact the heat exchangers. They are heat exchanging devices, and there may be fans. What we are seeing over here, the grayish area, are the fans that are placed on those pipes, and the pipes are being bent. So as far as the application is concerned, heat exchangers have got a huge application in heat transfer. So over here we are looking at the temperature profiles along the length of the heat exchanger. So on y-axis we have got the temperature, and on x-axis we have got the length of the heat exchanger. And over here we are considering two types of heat exchangers. This one is the parallel flow heat exchanger. This one is the parallel flow heat exchanger, and the second is the counter flow heat exchanger. We also have a third type, which is the cross flow heat exchanger. So in parallel flow, the two fluids, the hot fluid and the cold fluid, move in the same direction. They flow in the same direction as is being shown over here. In counterflow, whereas in counterflow the two fluids move at 180 degrees to each other. For example, the hot fluid is coming in and is then flowing in this direction, in positive x-axis direction, whereas the cold fluid will be moving in negative x-axis direction. So the two fluids move at 90 degrees to each other. Whereas in cross flow the two fluids flow at over here the two fluids, in counterflow the two fluids are moving at 180 degrees to each other, whereas in cross flow the two fluids move at 90 degrees to each other. So when we take a look at the profile, temperature profile in case of parallel flow, we can see over here that the temperature of the hot fluid, in fact there are four temperatures: hot in, hot out, cold in, cold out, right? We may call it TH in, TH out, T cold in, T cold out. So over here the fluid enters at the highest temperature, which we may call as THI or THN, and as it moves along the length of the heat exchanger, its temperature gradually goes down because it is giving away energy to the cold fluid, and since it is giving energy to the cold fluid, the temperature of the cold fluid is on a rise. So the temperature of the cold fluid increases from T cold in to some outlet temperature which we may call as T cold out. Of course, the temperature of the hot fluid which is going out cannot become lower than the temperature of the cold fluid going out of the heat exchanger. Now over here, when we talk about counterflow heat exchanger, the hot fluid enters at the highest temperature, we may call it as THI, and then it gives away energy to the cold fluid, as a result of which the temperature of the cold fluid goes up, and the temperature of the hot fluid will go down. So the temperature of hot fluid which is going out, over here the temperature of the hot fluid which goes out can never exceed the temperature of the cold fluid which is going out. But over here, the temperature of the cold fluid which is going out, can exceed the temperature of the hot fluid going out. The reason is that on its way out, the cold fluid is not exchanging heat with TH0, rather it is exchanging heat with THI, since it is a counterflow heat exchanger. So therefore its temperature may exceed TH0, but it will never exceed THI, of course, because on its way out it is not exchanging heat with TH out, rather it is exchanging heat with THN, and that is why the counterflow heat exchangers are considered to be more efficient as compared to or they are supposed to have a better performance as compared to parallel flow heat exchangers. Now moving forward, this is the figure taken from our book, that's figure 11.2 of Incorpora and DeWitt, and over here it shows concentric tube heat exchangers in parallel flow and counterflow. This is what we have just discussed. In figures A and B. So the two fluids are moving in the same direction, so that would be considered as a parallel flow heat exchanger, whereas over here the two fluids are moving at 180 degrees to each other, therefore it would be considered as a counterflow heat exchanger. Now over here in this figure 11.2 we are going to discuss cross flow heat exchangers. Now over here we are being shown 1, 2, 3, 4, 5, 6, 7, 8 pipes, and those pipes are such that they have been placed in a plate, or the plate has been fixed outside the pipes. So the length of the pipe goes in this direction, and along the length of the pipes there are several plates, and those plates would in fact act as fins. So there would be one fluid which would be flowing through the tubes, and its flow direction would be this one, or it may be exactly at 180 degrees. Now the other fluid which is flowing will pass through those plates, So the two fluids are in fact at 90 degrees to each other. So this would be an example of cross flow heat exchanger. Now this is also a cross flow heat exchanger, but this one does not have got those plates, rather it has got the tubes only. And we can see over here that there is a fluid which is flowing in this direction, the other fluid is flowing in this direction, same as this one, but over here the plates were providing it a particular direction. Now over here there aren't any plates that may provide this fluid a particular direction. So in that respect we call this fluid, so over here both fluids, in this particular case A, both fluids would be called as unmixed. Over here, unmixed refers to the change in direction. The fluid which is flowing through the tubes will have its direction because it has got a channel to flow through. So it will keep on flowing in that channel and its direction will not change. Similarly, the other fluid which is shown over here has got another channel which is provided due to those fins, due to those plates. So it will pass through those fins, it will pass through those plates, and it will then come out. So both the fluids have got a particular channel, both the fluids have got a particular direction. So we say that both fluids are unmixed. Over here, mixing does not mean physical mixing. Rather, mixing refers to the change in direction. Now in case B, the fluid which is passing through the tubes will remain flowing through the tubes in that particular direction. But the other fluid which is flowing in this particular direction along x-axis, it does not have this channel, does not have those plates, does not have those fins anymore. So it will, of course, it will flow, it will try to flow in this particular direction, but after a certain distance, it will not be able to keep its flow solely in this particular direction. So its direction will be in that x-axis direction, and a certain amount of it will start moving in other direction. So that is why we would call it that it is the cross flow heat exchanger with one fluid mixed and the other fluid unmixed. One fluid unmixed means this is referring to this tube flow, where the direction of the fluid through the tube will remain fixed, whereas this mixed is referring to this particular case where the fluid will not be able to keep that particular direction all the way through. Right? So both fluids unmixed, one fluid mixed, the other one unmixed. So that would be the two cases in cross flow heat exchangers. Counter flow out of all three means out of parallel, counter and cross flow heat exchangers, the counter flow is considered to have the best performance over others. Now over here we are being shown this particular heat exchanger, shell and tube heat exchanger, which we have just discussed a couple of slides earlier. And I have taken this figure from in Cropper and Dibit. It's figure 11.3 of our book, but it has a very interesting caption. It says it is a shell and tube heat exchanger, so which we have already discussed, so there is no point in discussing it again. With one shell pass and one tube pass. So over here we are discussing passes. We are discussing over here passes. So what does pass mean? Pass means that the shell side fluid will come in from here and then it will leave from here. It comes in from one side and then it leaves from the other side. So it flows in this direction. The shell side fluid flows in this direction, whereas the tube side flow will come in through this inlet and then it will flow through those tubes and then it will come out of this outlet. So that is the tube side fluid is flowing in this particular direction. So the tube side fluid is flowing in negative x-axis direction and is not changing its direction, and the shell side fluid is flowing in this particular direction, positive x-axis direction, or it may be the other way around. But the thing is that the shell fluid does not change its direction and the tube fluid does not change its direction as well. This is what we call one pass. This is what we call pass. Now let's discuss passes in a little bit detail. Now over here, which is 11.4, figure 11.4 of our book, it shows it says shell and tube heat exchangers, one shell pass and two tube passes. So over here you can see that when we talk about shell side fluid, so it comes in from one side and then it flows in negative x-axis direction and then it goes out. So the shell side fluid remains flowing in negative x-axis direction. The tube fluid comes in and then it flows in negative x-axis direction, and then the tube takes a bend, so it changes its direction and then it flows in positive x-axis direction and then it goes out. So this would be called as two tube passes. This would be called as two tube passes. So when we have more than one pass, the heat exchanger will not fully be parallel flow or counter flow heat exchanger. Rather, for the first pass, if you look over here, for the first pass, the two fluids are in fact in parallel flow, whereas for the second pass, the two fluids are in counter flow. So we will see how do we take care of passes. In fact, we introduce a correction factor, which we will see later. The second one says that two shell passes. So there may be one shell and there may be two shells, which would make it two shell passes. So the fluid on the shell side comes in, it flows in this direction, and then it comes out, and instead of going out, it is then entered into a second shell. So while it is in the second shell, its direction of motion becomes in positive x-axis. So that would be considered as two shell passes, and this would be the first tube pass, second tube pass, the third tube pass, and then the fourth tube pass. So the tube has got four passes. So there may be multiple number of shell passes and multiple number of tube passes. What is the reason of the passes? Of course, you would have figured out by yourself that we want more heat transfer in a less space. So that is why we introduce passes. We increase the number of passes. Otherwise, the length of the heat exchanger will become very large, and there might be a space constraint, or large lengths will introduce some other types of stresses as well. So this is about heat exchanger passes. This is the same thing shown, what we have just seen on the previous page. So it is the one shell pass and two tube passes, and in fact over here we have got multiple shell passes, in fact two shell passes and four tube passes. The next figure 11.5 of our book talks about compact heat exchangers. Compact heat exchangers are those that have a very good, that are compact, and the definition of compact is in terms of area, which we will see in a bit, and they are used for higher rates of heat transfer. There are various types that are being shown over here. The first one is fin tube. Let me first go over the definition. It achieves a very large heat transfer surface area per unit volume. So if in per unit volume the surface area exceeds 400 square meter for liquids and 700 square meter for gases, then that would be termed as compact heat exchangers. Termed compact heat exchangers, these devices have dense arrays of fin tubes or plates. So over here that we can see over here in this figure, these are the fin tubes. Over here the tubes have a non-circular cross section. Over here the tubes have got circular cross section. In B the tubes have got circular cross section, but the fins are rectangular. Over here the fins are circular. So there may be different types of arrangement in compact heat exchangers. The thing is that we put the fins over there so as to increase the heat transfer rate by a large number in a small volume. The next is then the plate and frame heat exchangers. They are also it is also a very important type of heat exchanger. In plate and frame heat exchanger, there are channels provided over here on the top and bottom. One for the cold fluid and the other for the hot fluid. These are the plates. 1, 2, 3, 4, 5. These are the plates. And some of the plates have got gaskets as well. The fluid, while it flows through those channels, through in fact pipes, also flows down as well along the length of the plate. Where the heat exchange takes place. So in fact its heat exchange rate is very high, and it is a very useful type of heat exchanger which is used in industrial applications. So for further details, I would highly recommend that you see a video on YouTube. There are various videos available, but for example you may refer to the engineering mindset video for this plate and frame, which is usually called plate heat exchanger, PHX, so that you get so that when you would be seeing that simulation, you will have a better idea of how the heat transfer takes place in plate and frame heat exchanger. This is another a picture of the same type of heat exchanger. You can see over here that these are all the plates, which are in fact very close to each other. They are not that far apart, and there are channels provided on top and bottom, for one for the hot fluid of course, and the other one for the cold fluid. And the fluid flows over those plates as well, so as to exchange heat from one side to the other. So I would highly recommend that you see that simulation so that you can understand it a little better. The next topic is fouling. Fouling is you know that when the fluids will keep on flowing inside and outside of the tubes, the particulate matter will start getting settled on the inner and outer surfaces of the tubes. So this process is called fouling, and when that matter would start getting settled down on the surfaces of the tubes, inside and outer surfaces of the tubes, for example, if it is a shell and tube heat exchanger, so then that additional substance will offer more resistance. So more resistance will reduce the heat transfer rate. So in fact fouling is something undesirable, but it is something which cannot be avoided. So fouling will take place with time, of course, but we need to clean that fouling over time as well. So let's see over here, it says the layer of deposits represents additional resistance to heat transfer and causes the rate of heat transfer in a heat exchanger to decrease. Of course, this is what I was just telling you. Now, why does fouling happen? There are different types of fouling. Precipitation of solid deposits in a fluid on heat transfer surfaces. For example, if it is water, so in water there are different types of undissolved solids. So they would also get settled down on either the inner side of the pipe or outer surface of the pipe. So that would get precipitated. So when it would get precipitated, it will offer additional resistance to heat flow, and that is called fouling. Or if the gases are passing through any tube, For example, in a 5-tube boiler, the hot gases would pass through the tube. So that will result in soot inside those tubes. So that soot needs to be cleaned over time. It may be due to the corrosion, of course, right? We all know what corrosion is, and other chemical fouling. There may also be biological fouling due to the growth of algae in warm fluids, and that must be prevented, of course. So any type of fouling is undesirable because it would result in an additional layer, and that additional layer will reduce the heat transfer rate between the hot and the cold fluids. Over here there are different fouling factors that are given over here over per unit of area. If you take a look over here, it says R double dash means resistance per unit area, and we can also see from the units, the regular units of resistance are Kelvin per watt. However, if it is meter square Kelvin per watt, so that is resistance per unit area that we have discussed in chapter number 3, thermal resistances. So over here there are various fouling factors that can be taken. However, they will vary with the type of the fluid, of course. But nonetheless, that is a good point to start with. So over here we can see this fouling taking place. So that fouling needs to be get rid of, because that fouling, I mean that layer of oxide, iron oxide, would in fact be posing more resistance to heat flow, and therefore it will result in less heat transfer rates. So fouling will in fact reduce the performance. It will degrade the performance of the heat exchanger. Over here we can see the soot. It's black. It may be in the form of mud, it may be in the form of deposits, it may be in the form of corrosion. There are various types of foulings. Now over here, if this is the heat exchanger, I mean this is the inner tube, and there is an annulus, and through the tube flows the cold fluid, and through the annulus flows the through the inside tube flows the hot fluid, and through the annulus flows the cold one. So then this is how the overall resistance or overall heat transfer coefficient or resistance would be written in this form. And what are those? In fact, if you take a look over here, there would be a resistance offered by the wall. A wall means the wall which separates the hot and the cold fluid, and there would be convection inside the inner wall, and there would be convection outside the inner wall. Right? So there would be convection inside inner wall, which would be 1 over HA, and there would be convection outside the inner wall between the inner wall and the cold fluid, so which would also be 1 over HA. The resistance of the wall will be a log of R0 over Ri over 2 pi KL, because this wall is cylindrical. So these would be the resistances that we will come across. So it would be 1 over HA between the cold fluid and the wall, and 1 over HA between the hot fluid and the wall, and this would be the resistance of the wall itself. For example, over here this would be log of R0 over Ri divided by 2 pi KL. So we may write it as so since this is resistance, so the resistance and U are reciprocals of each other. We have seen it in chapter number 3 that resistance Q may be written as delta T over resistance, whereas Q may also be written as UA delta T. So UA would be equal to 1 over resistance, or resistance would be 1 over UA. So therefore resistance is written over here, or rather resistances are written over here. So therefore on the left hand side we have 1 over UA. So we may write it as 1 over UA of the cold side or of the hot side. And of course both would be the same as long as the system is working under steady state conditions. So the same thing is written over here, 1 over HA, and then the resistance of the wall, log of R naught over Ri divided by 2 pi KL or D naught over Di, and the second convective resistance. This applies to clean surface. This applies to clean surface because there isn't any resistance due to the fouling which has been included over here. If we have an additional resistance due to fouling, of course that will be written as the fourth or even the fifth resistance on the right hand side of the equation. Now over here, coming from this point to here, in fact, if it is a thin walled cylinder, so D naught and Di would approximately be the same. If it is a thin walled cylinder, and of course the cylinder will be made of a highly conductive material. So so in the numerator it would be log of approximately 1, which would be a very small quantity, and in the denominator K, thermal conductivity, would be very high. So if this is the case, then this middle resistance which is offered by the material wall itself can then be neglected, and therefore we can write it in this form that 1 over Hi plus 1 over H naught will remain on the right hand side, and then areas will also get cancelled out. Why areas would get cancelled out? See, these are different areas. Over here we have got AI and over here we have got A naught. But what is the difference between AI and A naught? It is, the only difference is that of the radius or diameter. Now if the radii are approximately be the same, so then areas would approximately be same as well. So therefore AI would then be approximately same as A naught, and then therefore they can be neglected as well. They will not be neglected, rather they will be cancelled throughout the equation. Areas will be cancelled throughout the equation, and then we would have this form of expression. Of course this is not a universal expression, it has been reduced from this larger set of expression. However, if we have got fouling, then we would have those three resistances, 1, 2, 3 as usual, which we had seen on the previous page. Now in addition to those three resistances, this fourth resistance, which is the fouling resistance on the inner surface, and this fifth resistance, which is the fouling surface on the outer surface, will get added up, thereby reducing the heat transfer. And fouling resistance may be written as 1 over U dirty minus 1 over U clean, where U clean refers to the heat transfer or the heat exchanger without fouling, and U dirty refers to the heat transfer or heat exchanger with fouling.